Hello, my name is Nicholas Chamov from Paratools. I'm presenting the paper Identifying Optimization Opportunities Using Memory Access Tracing in OpenSHMEM Runtimes with the Tau Performance System. In this presentation, I'll briefly describe what OpenSHMEM is and why we want to track memory allocations and accesses within OpenSHMEM runtimes. I'll then introduce Tau, an open-source cross-platform performance monitoring tool, and describe the existing features of Tau that we make use of in this work. I'll then describe the implementation of two new features within Tau, memory allocation tracking on a per-object type basis, and memory access tracing on a per-object type basis. Using memory allocation tracking and memory access tracing, we identify object types within the Open MPI 4.0 implementation of OpenSHMEM, which are targets for optimizations to reduce per-node memory use. OpenSHMEM is a specification for an API for a partitioned global address space, or PGAS runtime and computational model. PGAS runtimes and languages differ from MPI and MPI-like runtimes that are commonly used in HPC. In PGAS, communication is accomplished through a partitioned shared memory space rather than through explicit two-sided message passing. A globally addressable memory, called the symmetric heap, is allocated, which is partitioned across nodes. Certain regions of that shared memory are resident on a particular rank or processing element in the OpenSHMEM parlance and can be accessed as local memory. Portions of the shared memory not local to a PE can be accessed through one-sided communication by making calls into the OpenSHMEM API to get, or read, or put, or write data to memory resident on another node without that node's synchronous participation. Atomic operations and collectives are also provided. As an example, consider this simple demonstration of a one-sided put operation. As in MPI, in which many ranks execute the same code but are distinguished by a rank ID, in OpenSHMEM, PEs are distinguished by a PE number. Here, the OpenSHMEM runtime is initialized, and each PE determines its PE number along with the number of PEs present in the application. The PEs each define a variable on their local stack, called source, and then collectively allocate memory on the symmetric heap. This is a symmetric, remotely accessible memory block. The memory block can then be used with OpenSHMEM communication routines. A pointer to this block is stored in the variable called dest. On PE0, a one-sided put is then performed, copying the value stored in the local stack variable source into dest. Once this put completes, it is accessible on PE1. Finally, a barrier is performed across all PEs. After the barrier returns, all local and remote memory operations issued by any PE have completed. OpenSHMEM has been proposed as a programming model for use on exascale systems. On such systems, applications will need to scale to millions of processing elements. However, future exascale systems are expected to have less memory per core than present petascale systems, as core counts on leading HPC systems have been doubling in 3.3 years, while memory size has been doubling only every 5 years. This presents a problem whereby, even if an application itself may be designed to scale to such large PE counts, the underlying runtime may use memory in such a way that limits the scalability of applications built on top of it. In particular, by keeping internal arrays on every PE with size proportional to the number of PEs, an OpenSHMEM implementation may limit its scalability. In this work, we build tools to analyze one such OpenSHMEM implementation, the OpenSHMEM component of Open MPI, and analyze, first, whether scalability issues of this type exist, and, two, what optimizations may be possible to alleviate such scalability issues. To accomplish this analysis of the OpenSHMEM runtime, new tools were needed. Existing general-purpose memory tracing toolkits, such as Valgrind and ThreadSpotter, impose overheads of 10 times to 30 times for single-node applications, and can impose even higher overheads for distributed applications. Additionally, existing general-purpose tools identify memory allocations and accesses by address or line number of code, but we want to identify allocations and accesses by data types, aggregating allocations of and accesses to different objects of the same data type. In this way, we can identify data structures with memory scalability issues. Tau supports two primary approaches to measurement. Profiling characterizes the behavior of an application in terms of aggregate performance metrics. Profiles are typically represented as a list of various metrics, such as wall clock time, and associated statistics for all performance events in the program. The most basic and standard type of profiling is called flat profiling. If tau is being used for flat profiling, performance measurements are kept for interval events only. For instance, flat profiles will report the exclusive performance, such as time for a routine, say A, as the amount of time spent executing an A exclusively. An alternative to flat profiling is call path profiling, which disaggregates performance data according to the unique call graph through which a given function or kernel came to be executing. While profiling is used to get aggregate summaries of metrics in a compact form, it cannot highlight the time-varying aspect of the execution. To study the post-mortem spatial and temporal aspect of performance data, event tracing is used, whereby each individual entry to or exit from a function or kernel is recorded along with a timestamp and potentially other metrics. We use both approaches in this work. Using the different instrumentation and measurement techniques available in tau, and by measuring different metrics, tau is able to answer many questions about the execution characteristics of applications. The performance questions that tau can be used to answer include: how much time is spent in each application routine and outer loops, and what the contribution of statements within those loops are? How many instructions are executed in those code regions, and what are the I/O characteristics of the code, like the extent of data transfer between a host and GPU, and the contribution of each phase to the program. Tau can also be used to answer questions about how the application scales, such as how the runtime changes as the data size or core count changes. And, most relevant to this project, tau had the existing ability to answer questions such as what is the memory usage of the code overall, and when and where is memory allocated and deallocated. However, these existing memory usage features were inadequate for the analysis we wished to perform on OpenSHMEM runtimes because they were focused on determining the computational context of memory allocations, such as determining in what function or on what line of code a particular allocation or deallocation occurred. Tau supports several event types. These include interval events, which represent measurements taken between begin and end events. For example, when measuring the time spent in a function, this is recorded as an interval event which begins on entry to the function and ends on exit from the function. Atomic events represent a value at a particular moment in time rather than over a defined interval. We use these to record memory allocations, deallocations, and accesses. Context events combine an atomic event with its computational context, such as those that occur during a particular interval event. For example, this could show which memory allocations occur within a function. This example of output from tau shows the distinction between interval events and atomic events. Interval events show duration, while atomic events show extent of variation. Here, the interval event shows time spent in MPI functions, while the atomic events show memory usage at particular moments in time. Context events disaggregate atomic events based on the context in which they occurred. Here, the events recording memory usage are disaggregated according to which function was being entered when the memory usage was recorded. To collect the data required for analyzing the memory usage of the OpenSHMEM runtime, we used library wrapping. With library wrapping, tau provides a library which implements its own versions of malloc, free, and other system memory calls, which are substituted for the system versions by using the LD preload mechanism to cause the wrapper library to be loaded before the standard library. Each wrapper starts a tau timer, records a context event indicating the size of the allocation or deallocation, calls the real underlying system version of the function in the standard library, stops the timer, and returns. A similar technique is used to wrap OpenSHMEM API calls. However, different versions of the OpenSHMEM standard, and different implementations, have differences in the names of functions and of the types of arguments to those functions. Therefore, instead of using a manually written wrapper as with wrapping malloc, with the OpenSHMEM library the wrapper is generated at configure time. During configure, tau parses the shmem.h header which declares OpenSHMEM API functions. It then generates a wrapper library containing wrappers for each function defined in shmem.h. For each function, a timer is started and the underlying OpenSHMEM library call is made. The timer is stopped at exit. For those functions which represent communications, a context event is recorded indicating the size, source PE, and destination PE for the communication. Used together, these features allow Tau to determine memory usage of the application overall, and can attribute memory usage to specific OpenSHMEM API calls, but it still does not tell us where in the runtime the allocation occurred, or of what data type. To measure memory allocations and deallocations based on data type, we extended Tau's memory allocation tracking support with Allocation Classes. An allocation class represents an interval during which allocations that occur will be attributed to a particular type. This enables tracking of hierarchical allocations, which are used to track the allocation of both parent objects and their members. These allocations are recorded alongside performance data in the Tau profile. Consider the code example shown. In this example, an allocation of type A is started with size 10. During that allocation, another allocation of type B is started of size 25, which is then closed. The allocation of type A is then closed, and another allocation of type B in size 10 is opened and closed. The consequence of the allocation of type B inside an allocation region of type A is that 25 bytes of B is attributed in the profile to B within A, out of the total of 35 bytes of type B that are allocated. The allocation regions just described are designed to match the object system, OPAL, of the Open MPI runtime, so that centralized instrumentation of the Open MPI memory manager can capture memory allocations of most objects and their members. In Open MPI, most allocations go through the OPAL obj_new function. Some members, such as arrays and network drivers, are allocated outside of the object system. To handle those types, we allow for a memory allocation region to be reopened without actually recording an allocation, so that child allocations can be attributed to their parent, even if the allocation occurs outside the standard object system. To track flat allocations of most OpenMPI runtime types, without regard to members of objects, requires adding only one line of code to the OpenMPI runtime. Tracking hierarchical allocations requires adding only two lines of code, one to open an allocation region on entry to the OPAL obj_new function, and one to close the allocation region on exit. Objects allocated in the constructor of the object are then automatically attributed to the enclosing region. Using allocation regions, we can determine the memory allocated by a particular object type within the OpenMPI OpenSHMEM runtime. For example, in this chart, we can see that in this application on PE0, 158,760 bytes were allocated for objects of type MCA base VART, all of which occurred during the call to shmem init, which initializes the runtime. Note also the use of hierarchical allocations. For example, the arrow here indicates a measurement of the total allocations of objects of type ORT namelist T as a member of OSHMEM group T objects. To demonstrate this approach as applied to memory scaling in the OpenMPI OpenSHMEM runtime, we ran an OpenSHMEM benchmark application, GUPS, with memory allocation tracked using Tau for a varying number of processing elements between 16 and 1024. The results for a subset of object types whose child array allocations were manually instrumented is shown here. These results answer the first of our two questions in the affirmative. There are object types in the OpenMPI OpenSHMEM runtime, the memory growth of which could serve as a bottleneck, limiting scalability at large PE counts. The object types identified here store data on other PEs and groups of PEs. These objects grow with the number of PEs, and the OpenSHMEM runtime stores a copy of each object on each PE. Thus, the total memory consumption of these object types grows with the square of the number of PEs. Looking at all runtime types, including those not manually instrumented, reveals that OPAL value T has by far the largest total allocations. Usages are spread out as children of many other object types. However, total allocations does not give us the whole story. Recording total allocations does not let us distinguish between data types whose objects persist for the lifetime of the application and others, such as objects which are used temporarily during initialization or during specific API calls, or those which are allocated and deallocated repeatedly during the course of program execution. To distinguish between these cases, we'll need to use phase-based profiles or traces. In this analysis, we opted to use traces in the OTF2 format. To capture cumulative allocations at a given moment, we added an additional instrumentation point in the OpenMPI OpenSHMEM runtime, in the OPAL obj run destructors function. This function is called when an OPAL object is freed. These instrumentation points first open a deallocation region, call the object's destructor, and close the deallocation region. Whenever an allocation or deallocation region is closed, an atomic event is triggered recording the cumulative size of currently extant allocations for the given object type. By doing this, we can track the time course of cumulative allocations of different memory types during program execution. For example, this view shows the allocations of opal value T objects during an execution of GUPS on 128 PEs. The bottom view is zoomed in along the y-axis to show detail during initialization. We can tell from this view that some opal value T objects are allocated and then deallocated during SHMEM init, but that the bulk are allocated at the end of initialization and then persist for the remaining lifetime of the application. So we have now identified that a memory scalability problem exists in the Open MPI OpenSHMEM runtime. We now want to know how that problem could be addressed. One possible optimization would be to share data structures across PEs within a node. This could work if they are the same within a node, which could only be true if they are not written to after runtime initialization. That is, they need to be not altered by API calls made by the program. To determine which data types are written to during different phases of program execution, we implemented a tracked allocation. As was the case with tracking memory allocations, we can instrument the Open MPI OpenSHMEM runtime to trace reads and writes, for most object types, with only a minor change to the runtime code. Here, we replace calls to malloc with tau-tracked malloc. This allocates memory within tau-managed pages to enable tracking reads and writes to those pages. To implement memory access tracing, we use Linux user-level fault handling. Tracked memory pages allocated through tau-tracked malloc have their permissions set through mprotect to prevent either reading or writing to the page. Therefore, whenever a read or write is attempted, a segmentation fault occurs. Tau registers a handler for the segmentation fault signal, which changes protection to read-only and single-steps the processor to attempt to retry the memory access. If this was successful, then the access is known to be a read, the access is recorded as a read, and then memory protection is restored to prohibit both reads and writes, and the program execution continues. If it was unsuccessful, then the access must have been a write, in which case permissions are changed to allow both reads and writes, the processor is single-stepped to allow the write to succeed, and permissions are then restored to prohibit both reads and writes, and program execution continues. This instrumentation has high overhead, but this overhead can be limited by restricting memory access tracing to only specific runtime object types of interest. We repeated the earlier test with the GUPS benchmark on between 16 and 1024 PEs. 5 runs were performed. During each run, only one object type was tracked, which corresponded to the 5 most memory-consuming OpenSHMEM runtime objects identified by allocation tracking. Separate measurements were performed by program phase, of which 3 were considered. Runtime initialization, which corresponds to execution prior to return from SHMEM init, application execution, and runtime finalization, which corresponds to execution after entry to SHMEM finalize. This analysis revealed that of the 5 most memory-consuming data types, only the pointer-to-pointer to OMPI proc-T was written to during application runtime. Thus, for this application at least, the other object types are potentially targets for optimization by sharing across PEs within a node. To compare the performance of our targeted approach versus whole program tracing, we ran the GUPS benchmark on 16, 32, 64, and 128 PEs in 3 configurations. First, uninstrumented. Second, with one data type, OMPI proc-T, instrumented with tau. And 3, with Valgrind's memcheck tool, which instruments all memory accesses. On 16 PEs, the overhead of tau instrumentation increases end-to-end runtime by 2.3 times, increasing to 3.9 times on 128 PEs. For Valgrind, instrumentation increases end-to-end runtime by 15.2 times on 16 PEs to 25.3 times on 128 PEs. While tau cannot gather the variety of data that Valgrind is capable of, for example, it cannot diagnose use after free bugs, for the type of analysis needed to identify optimization opportunities within OpenSHMEM, it can collect the required data with 6 times lower overhead than Valgrind. To conclude, we have developed a tool which can track both memory allocations and memory accesses during execution of OpenSHMEM applications. Our tool requires very little modification of the runtime. With no runtime instrumentation, tau can capture runtime allocations by source line of origin, while by adding 4 lines of code to the runtime, we can also capture the data types of allocated objects. And with 2 more lines of code, we can also capture reads and writes for specific data types. Using this tool, we have analyzed the Open MPI 4.0 OpenSHMEM runtime and identified 4 data types which limit scalability and which may be targets of optimization for running at the scale of millions of PEs. Tau is available for download at tau.uoregon.edu, and the source of our lightly instrumented Open MPI runtime is available on GitHub at the listed address. If you have any questions about this presentation, the use of Tau with OpenSHMEM applications, or any other aspect of Tau, please contact us by email at support@paratools.com. Thank you.